Good afternoon, everybody. It is once again a pleasure for me to welcome you through of the Department of Chemistry, the Universidad Autónoma Metropolitana, to the first international webinar del Área Académica de Química Analítica, aplicación de las herramientas de inteligencia artificial en química analítica. This webinar is organized by Dr. Jorge Juárez Gómez and Dr. Daphne Saraya Guzmán Hernández. We remind you that you can follow the event live through the department social media channels on YouTube, Facebook, X, and the official website of the Department of Chemistry displayed on the screen. Remember that during the conference, in the chat, an attendance form will be posted to send your certificates. Now, without further ado, it is my pleasure to introduce our next lecture titled Machine Learning Methods for Surface Enhanced Raman Scattering Sensors, which will be presented by Dr. Jean-François Masson. It is worth noting that he is full professor of chemistry at the Université de Montréal. He is graduate of Arizona State University, PhD, and Georgia Tech postdoc. His expertise encompasses biosensing with plasmonic materials, instrument development, surface chemistry to minimize bioflouring and detection of proteins and drugs directly in crude biofluids. He has published more than 100 research articles, and his research has led to filling more than 10 patents on diverse instrumental, material, or surface chemistry innovation for biosensing. Dr. Jean-François received several awards, including the Thomas Hirschfeld Award 2005, NSERC Discovery Accelerator 2011, the Fred Beamish Award of the Canadian Society for Chemistry 2013, and an Alexander von Humboldt Fellowship Germany 2013-2014 for research at the Max Planck Institute. In 2018, he has named in the list of the top 40 analytical science under the age of 40s. He is currently an associate editor for the Analysis of RAC Publishing. Welcome, Dr. François Masson. Now I give you the opportunity to begin your presentation, please.
Okay. First of all, muchas gracias por la invitación a presentar nuestra ciencia, pero mi español no es bueno por hablar en español ciencia. So I will switch to English. Thank you very much. This is a pleasure to be able to share our work today. So my research group works on different aspects of instrumental analytical chemistry. So we work on designing instrumentation, designing nanomaterials. We perform surface chemistry to be able to detect analytes. We use spectroscopy, and we develop applications that are oftentimes field deployed. So you have one example here where we have a sensor for detecting explosive in water that we deployed in the Canadian North. And also, I will speak a little bit about how we can use analytical chemistry to grade maple syrup in this presentation. The main technique we use is localized surface plasmon resonance. This technique actually is when light is or it's in proximity of a nanomaterial, the electrons of the material can start to oscillate due to light field. And that oscillation can lead to a resonance that can be seen as a plasmon absorption band. Here we can see. And depending on the molecules in proximity of these nanoparticles, we can see a change in color of the absorption band. One other way to use that is to create surface-enhanced Raman scattering sensor. So Raman spectroscopy is a technique where you get the vibrational fingerprint, where the spectra here shows vibrations of the molecule at different frequencies. And these frequencies are indicative of the molecular nature of a molecule. However, Raman spectroscopy is very, very weak. But if you use nanomaterials, the molecule, when it enters the plasmon field here, which is the resonance of the electron. So when you have the light, the electrons will oscillate and will lead to a very high field in this location here. When the molecule enters here, it will experience very high enhancement. So we can now use surface enhanced Raman scattering to detect very tiny concentrations of molecules. Tying all of this together, because Raman spectroscopy gives rich, complex data set, we combine that with machine learning. So in my field of work, there's two main aspects of machine learning that is quite useful. Since we need to make nanomaterials, we can use machine learning to correlate optical data, so essentially the spectrum that we acquire, with the synthesis condition to be able to optimize materials. And I will show one example of that later on. We can also correlate the optical data, so the spectra we collect, with the properties or the classification of molecules, and I will show a few examples of that as well. In the case of Raman spectroscopy, that we'll spend most of the presentation discussing about. So since the spectra are essentially a vibrational spectra that contains a lot of information, we can use different strategies to be able to process the data. So we can use supervised algorithms. We need to provide the labels to data, and we'll try to maximize recognition of features associated to that label object. So essentially, the biggest use for it is to assign spectra to its identity or predicting a property. In the case of Raman, if we have an unknown spectra, we can assign its molecular identity by using a trained algorithm where we train the algorithm with known spectra of different molecules, and we can identify which one the unknown is later on. We can also use unsupervised algorithm. In this case, we don't have the information on what molecules we're looking at, but then we want to classify between different groups or different categories. So one of the biggest tasks in Raman spectroscopy is to cluster data. So essentially is to separate data into categories. For example, is this person healthy, or is this person has a cancer in the case of, for example, a clinical assay? Increasingly and more recently, the idea of using reinforcement learning is becoming more useful in analytical chemistry. In this case, we can train an algorithm to maximize the output by applying a bonus or a reward for let's say the output or the sensing. So in one case, we could say, okay, we want to maximize the Raman intensity or the sensitivity of a sensor to a molecules, and then we can use reinforcement learning to change, for example, the material fabrication conditions to reach that optimal property. And I will show one example of that towards the end of the presentation. So the first type of example, and this is an example from the literature, it is to be able to discriminate between groups, so to use clustering of data. So in Raman spectroscopy and surface enhanced Raman spectroscopy, we can acquire Raman vibrational spectra from different groups of, in this case, it was bacteria, in the case of that published paper from a different group, and then use a deep learning algorithm to be able to create a separation between bacteria that are susceptible to antibiotics, bacteria that are resistant, and the control bacteria data set. So in this case, we could be able to use new data. For example, we use a bacteria from a cultures from an individual and see if the bacteria is resistant or not, and be able to prescribe the proper antibiotics in this case to someone. So in my research group, we have used this type of technologies to be able to discriminate between COVID patients. So what we have done is that we've collected serum from individuals that were infected by COVID, and we've mixed it with silver nanoparticles in this case. And then we've put them on an aluminum glass, and then we use the Raman laser to collect Raman data, and compare between different groups of individuals. So the groups were people that were COVID negative and people that had COVID 4 weeks prior to the test and 16 weeks prior to the test. What we've done is that we pre-processed and pre-treated the source spectra by doing a baseline subtraction using asymmetric least squares. And we scaled and normalized the data to be able to provide a homogeneous data set to the machine learning algorithm. So the data set that was normalized and pre-processed looked like this. And we see that in some cases, the Raman bands do not change much between the control and the COVID positive individuals. But in other cases, we do see some differences between the control group and the COVID positive that can be interpreted to classify the data between COVID positive and COVID negative individuals. So the first algorithm we've tried is to use principal component analysis. This is a unsupervised algorithm that will reduce dimensionality of the data, and we'll try to create new features or new axes of the data to maximize variance. So in this case, we see that there is some separation between the negative in pink and the positive in red and green, but the difference is not big enough to have a definitive conclusion between the control group and the COVID positive group. So in this case, unsupervised algorithm did not provide sufficient discrimination between the two groups. So we can apply then in the second step a supervised algorithm, canonical variance analysis. And in this case, the combination of the two was able to create groups that were quite well separated between the negative controls in pink, the 4 weeks after being infected in green, and 16 weeks after being infected in red. So in this case, the semi-supervised algorithm was able to classify if someone had COVID, and we had an indication of when COVID actually happened by using Raman spectroscopy. A different type of approaches that we're quite interested in at the moment is to be able to understand and analyze chemicals being secreted by cells. So if you have, for example, a cell and you provide a stimulation, and that stimulation could be like a drug. So you give a medication to someone, the medication will have an impact on the cell. And in this case, it could lead to the release of molecules from the cell. That will be an indication if the treatment is successful or not. If the molecule is released, it can bind to our surface-enhanced Raman substrate and give a Raman signature that is distinctive of that molecule. So we need to make these fibers to be able to place in proximity of cells or, for example, neurons. And we make them by pulling a glass fiber to a tip diameter of less than 1 nanometer. And then we coat that fiber with a block copolymer. The block copolymer is composed of polystyrene and polyfluorovinyl pyridine. That unit of polyfluorovinyl pyridine binds really well to glass. And when it binds to glass, it forms a single layer of the polymer. And that polyfluorovinyl pyridine group likes to bind as well to gold nanoparticles. So when we dip the fiber in gold nanoparticles that has citrate cap on it, it will form a dense layer of well-dispersed nanoparticles. So this fiber here now becomes a very good Raman substrate because of the presence of the gold nanoparticles, but also its tiny size. Being less than 1 micron in diameter, we can place it very close to cells or neurons. So in one case that we like to study is neurotransmission. In the case of neurotransmission, there is some evidence that there are more molecules than dopamine and serotonin, for example, involved in neurotransmission. But current techniques using electrochemistry sometimes cannot capture the complexity of neurotransmission. So we're trying to use these type of tiny fibers, place them very, very close to neurons that are, for example, in the cultured Petri dish, focus the Raman laser on the tip, and see when we stimulate the neurons if they release neurotransmitters. To stimulate the neurons, we can use a different potassium chloride concentration, and that will depolarize the neurons, leading from a low secretion to a high secretion, seen by different bars here. So bars are detection events, and we can see the difference between the detection events between the low and the high potassium concentration. So when we turn on the laser, we see sometimes no signal, and sometimes we do see Raman signal appearing. And this is for a pure solution of dopamine. You can also tell that the signal will change. So the Raman spectrum is not the same every time we detect a dopamine molecule. This is because the dopamine molecule can bind in different orientation. So depending on the orientation of the molecule, it presents a different profile to the nanoparticles, and it will lead to different Raman vibrational spectrum. So that means each spectrum will be different, and thus it presents a more complex data set to be able to interpret. In some ways, when the molecule binds on the nanoparticles, it's a little bit like taking a picture of someone. If you take the picture from the front or from the back, the picture will be different, but it's still the same person. So the molecule, depending on its orientation versus the nanoparticles, will present a different vibrational spectra that will be captured with the Raman signal. So that puts a lot of constraint on the data processing. So what we can do is we can take libraries of spectra of Raman spectra of neurotransmitters. So in this case here, we have a library of dopamine, glutamate, ATP, acetylcholine, and GABA. So these 5 molecules are playing key roles in neurotransmission, and thus we want to detect them in proximity of cells. So one of the key features is that this is the average spectrum, but every spectra we can collect afterwards will be slightly different, such that we need to have more advanced data processing technique. So what we can do is we can use the raw data. We have to remove the cosmic ray to make sure that there's no artifacts in the data. We can smooth the data using a Savitsky-Golay smoothing algorithm. So this algorithm will use a moving average to reduce noise on the data. We can use an AirPLS baseline generation. So that will use an algorithm that will use nonlinear baseline generation. And then we can subtract that. And then we can see if there is signal, because one of the biggest challenges is that you don't want to analyze noise. So every Raman spectrum that do not have signal, you don't want to interpret that one. So you can generate a threshold and then count the peaks over the threshold to see if it's real data or not. So if you see peaks, you can say, yes, this is an active spectrum, and then you can process it. If no, well, it's an inactive spectrum, and then you can put it in the garbage bin. So this is the algorithm we have and the GUI we have developed in our lab, where we can adjust a number of parameters that I will not explain here due to for the sake of time. But what we have here is we have, for example, here a spectrum that has no Raman features because the baseline correction here in red does not show any peaks that are significant above the noise. But in other cases, like in this one here, we see a number of peaks that exceed the threshold in red. And thus we can say that this spectrum here, number 73, is an actual spectrum, and there was signal. Then we can correct the baseline using these features, and then we can have a normalized and a baseline corrected Raman spectrum. Then we use a convolutional neural network to be able to process the data. So the way we do that is that we use these training sets where we acquire Raman spectra of pure compounds. So in this case here, it was ATP. Then we optimize the neural network to be able to recognize ATP from other analytes. And then when we have new data, which are, for example, the unknown data that we can acquire in a new experiment, then we have the image, so which is the spectra, that we can assign the label, which is the molecular identity. So we do the inverse process to assign the proper label or the proper chemical name to the spectrum. So the way we do this is that we use a convolutional layer applying a 2x1 weight filter. So we reduce the dimensionality of the data a few times. Then we have a densely connected layer that is followed by a second one. So it's a deeper learning way to perform the analysis. And then we apply a softmax to convert the output of the layer into a probabilistic output. And we also apply dropout to avoid overfitting. So the results of that is that we acquired about 100,000 Raman spectra for this data set. We split it into a training set of about 70,000 and a validation set of about 30,000. And then here what we have in the confusion matrix is the proper assignment in the diagonal line, where we have about 90 to 95% proper assignment for all the neurotransmitters. The only exception here is glucose, but glucose is very difficult to measure with Raman spectroscopy, so the signal is very weak. So it's not a common contaminant, and thus it should not pose any issue in the algorithm. So one thing that we can do then is we can place the sensor next to neurons, and then we can measure the basal concentration of neurotransmitters. We see here for dopamine and glutamate, we don't have much signal in the resting stage. But once we depolarize a neuron, so once we excite a neuron with potassium, we see lots of signal, and we see a higher signal at this point here that shows that there is co-release of the two molecules. And then when we go to repolarization stage, so this is the normal resting stage, we see that there's fewer events at that stage. So what it shows here is that we can detect multiple neurotransmitters at the same time in cultured neurons. The only thing is that cultured neurons is not a representative way the brain works, because there's not the synergy between neurons. So what we want to do is we want to move to a more complex model. So we want to move to a model where we can insert these fibers inside brain tissue, but we need to insert them at a depth of about 80 to 120 microns. And this depth is necessary because once we slice the brain tissue, there will be dead tissue here on the top. So once the action of cutting the brain tissue will, of course, kill some of the neurons at the top, but the ones in the middle here will be healthy. Using potassium is not also very elegant because it's like using a hammer on the cell, so it will essentially force all the molecules to come out. So we can use more elegant methods, for example, using optogenetics to be able to monitor the Raman signal inside brain tissue. So in this case, we can turn on once again the laser on the fiber that is inside the brain tissue. We can measure the resting stage, so the normal stage at this moment. So we see a few signals coming in and out. And then in a few seconds, we will turn on the blue light to be able to excite the neurons. So the baseline will go up, and then we'll see a burst of signal for about 2 seconds that is coinciding with the excitation of the blue light. So the baseline will go up about now, and then we'll see the burst of light in this moment here. So this actually shows co-excitation, coincidental excitation and detection of neurotransmitters in brain tissue using Raman spectroscopy. But the biggest challenge is that as soon as you put the fiber in the brain tissue, the signal goes down very much. So if we take the Raman signature here, so this is outside the brain tissue, far from it, we see a large signal. As soon as we touch here in step 3, the signal goes down. And as soon as we insert the fiber in the tissue, we see that the signal decreases by about 80 to 90%. So the brain tissue is very, very scattering at the Raman wavelength that we use. So we use a visible 633 nanometer laser. And that means we can't efficiently detect neurotransmitters in the brain tissue. So we need to optimize that. So one way to optimize this is to use short-wave spectroscopy. So we have constructed a microscope that can excite neurons or excite the Raman at 1064 nanometers. But we need to create new nanomaterials to be able to have optimal analytical sensitivity at this wavelength. So one of the key concepts that we're exploring at the moment is to create a self-driving analytical chemistry lab. So the concept of a self-driving lab is to use robotics and computer science to be able to control key steps in the execution of experiments. In one embodiment, in one way to do it, you can use physical robots that will move solutions, or that will inject solutions mechanically, and that will be able to create, for example, nanomaterials or run analytical chemistry. In a different way, and the one we prefer, is to use fluidics to be able to pump reagents, pump analyte in tubing, and be able to create the materials we need, but also to functionalize them and to be able to create a system that will be autonomous. In this self-driving lab, the concept of using machine learning becomes critical. In this example from the literature, the authors were able to use spectroscopic data to control in the feedback the manufacturing conditions. So in this case here, it was the synthesis of silver nanoparticles. And here we have a set of reagents that were pumped at different flow rates. And the flow rates was controlled by a Bayesian optimization algorithm to be able to use the data from UV visible absorbance to control the pumps to optimize the synthesis conditions to a key feature. In this case, it was at which wavelength the particle absorbed. So we want to apply this because in our lab, we synthesize for analytical chemistry purposes gold nanostars. So nanostars are tiny nanoparticles with very long spikes, but typically we make them in batch. So we make a beaker of them. It takes about 2 to 3 hours to synthesize the particles, and the batch-to-batch reproducibility is actually not very good. So what we want to do is we want to use pumps, a little bit like HPLC pumps, where we pump fluids all together inside tubing, and then be able to synthesize these nanostars in flow. So when we compare the batch growth and the flow synthesis, the batch growth does not lead to the same wavelength of absorbance compared to flow synthesis. So there is a difference in the flow synthesis method that provides us a capability of creating nanoparticles that are closer to the intended wavelength of 1000 nanometers. But why? So we've investigated some of the aspects because using the pumps, we can control how quickly the fluid is being mixed. And here we have an example where the flow rate will have an impact on the synthesis method. So the flow rate will change how the molecules are being mixed in the tubing, and that will change essentially the particle growth and control the analytical properties of these particles. So at low flow rate, we get mostly spheres, and at high flow rate, we get these pointy particles that we call nanostar. So in this case here, just by changing the pumping speed, we can control the absorbance wavelength of these nanomaterials quite linearly. We can also control the shape of the particle by controlling the flow rate of the reagent. So in this case here, we can change the flow rate of silver nitrate. So silver nitrate is essential as a shape directing agent. So the silver nitrate will bind on the gold nanoparticles on some of the facets and will favor the growth of them in one direction. So by adding more and more silver nitrate, we get particles that are a bit larger, but also to have more spikes. So the spikes are the features that we want to have in surface tense Raman spectroscopy to maximize the sensitivity. So by controlling the flow rate of silver nitrate, we can control the plasmon wavelength, and then we can also control the Raman intensity doing so. One of the key features is essentially the same principle as HPLC. By using accurate pumps, we have very little error on the synthesis reproducibility. So when we did in batch, we had very large error bars on the plasmon wavelength that we would get. But by using these pumps to synthesize the particles, we get a much narrower distribution of wavelengths. And thus it provides a more robust analytical material for us to work with. So now we can use machine learning to be able to self-drive this synthesis. So while the original data published in the literature has used Bayesian optimization, which is a supervised learning method, We aim to use reinforcement learning to classify and control the process. So we are in the actual process of developing this reinforcement learning agent. So the agent is the tool that causes an action on the system. So an action can be a change the flow rate of silver nitrate. That will lead to a change in the environment, and then we can apply and reward and measure the state of the reaction by measuring the UV-vis absorbance, for example, to further train the agent to be able to control the synthesis of these materials to the desired wavelength. So what we have done now is to create a inflow analytical lab. So we have the pumps that flows in the reagents. We have a UV-vis cell to measure the UV-vis spectroscopy of the material. We can add a fifth pump here to add the analyte and measure in flow this analyte using Raman spectroscopy. By doing so, the time from the pump to the UV-vis is 0.2 seconds, and it takes another 0.2 seconds to add the analyte. So in less than 1 second, we can do the full synthesis of the material and measure the analyte inline. We can apply this reinforcement learning feedback loop to be able to control this whole setup to maximize the output, which in this case will be the analytical sensitivity of the Raman signal. So in the early stage, we did change the pumping speed of the silver nitrate to create the nanostars, and we can see that there's an increase in the Raman spectroscopy if you increase the silver nitrate, showing the proof of concept that we can measure inline the measurement of the Raman spectroscopy. So in the last segment of the presentation, in maybe the next 10 to 10 minutes or so, I want to change subject. So maple syrup is one of the hallmark food product of Canada. So maple syrup is made out of the maple trees. And at the end of winter, when the maple tree wakes up from hibernation due to the winter cold, there will be a movement of sap. At night, the sap will go up to the tree branches, and in daytime, it will go back down due to capillarity and the change in temperature. So that creates essentially a pump in the tree to wake it up. And the sap here is full of sugar. So we can collect the water and boil it down until it reaches 66% of sugar. So this is the official definition of maple syrup. Just to give you a bit of an idea, so about 80% of maple syrup in the world is produced in Canada. And out of that, about 75% or 90% of the Canadian production is done in Quebec, so the province that I live in. So, and it equates to about 300,000 barrels per year. But we need to analyze maple syrup. So the current analysis that is done is the measurements are based on transmittance, sugar content, and professional tasters. So there's individuals, people that their work is to taste maple syrup and give it a classification. One of the issue at the moment is that due to climate change, the late season harvest has become a little bit more irregular, and it can change the taste profile of the maple syrup, and such that it can be declassified with the so-called body taste. Essentially, the body taste is a maple syrup that tastes a little bit more musky, mushroom-like, so something that is quite different from the typical taste of maple syrup. But there's a technological gap to assist the producer and the industry in that to identify these batches of maple syrup with a different profile. So what we want to use is to use the concept of a plasmonic tongue. So a plasmonic tongue is a way to use analogies with the human tongue. So when we taste something, the taste buds will give a signal, a complex signal that the brain will associate to a flavor. In our case here, we use the simplest plasmonic tongue. So we use a single taste bud, where we have gold nanoparticles. And in maple syrup that has off flavor, there's some molecule that can bind to the nanoparticle. And if the particles are covered with these molecules, they will aggregate. By aggregating, they will change color. So in this case here, we can work the stoichiometry to be able to distinguish between normal flavor that do not have these molecules to off flavor that have these molecules. And the color change will be from red to blue, or from an absorbance standpoint, it will be from 520 nanometer absorbance to about 625 nanometer absorbance. So we can distinguish between off-flavored maple syrups and normal flavor maple syrups by using a differential absorbance or by using the naked eye by seeing here a negative sample will stay red and a positive will turn like a blue-gray color. So we've validated that with a few samples here, but we've increased that to about 2,000 samples in 2018, where about half of them were regular tasting and the other half was off-flavored maple syrup. And we were able to detect the off-flavored with 98% sensitivity, which is great, but only 70% selectivity, which means that 30% of the positive test was from normal maple syrup. So we decided to increase the amount of maple syrup analyzed in 2019. So we've received 30,000 samples covering the broad range of categories of maple syrup. So this is what my laboratory looked like at the moment. So this is about 10,000 samples. So we received about 3 times more. So there were samples from the floor all the way to the ceiling of this lab, and we've tested them all. And what we see is that with the different categories, we don't see a clear separation because using a single taste bud is not sufficient to have a clear distinction between all of the categories. And we try to apply more complex algorithms like neural networks, support vector machines, but it didn't significantly improve the outcome. One of the issue as well is that if you test the maple syrup, it's done after all the efforts were deployed. So it's done when the producer has taken all the steps to make it, so it incurred all the cost. So there's not a big advantage of detecting maple syrup flavor defect. So the biggest challenge will be to detect the sap. And to detect in sap, what we've done is we did a titration-based analytical chemistry, where we add the nanoparticles in a cuvette, we fill the syringe with maple sap, and then we add dropwise the sap to the syrup until the color of the solution turns blue. We can also measure it with a spectrometer. When it turns blue, we calculate the volume added, so in a regular titration-like fashion. And then we can correlate that using a mathematical model that use ordinal mix effect principles that can correlate the number of drops we've added with the transmittance of the maple syrup, with the outcome of the maple syrup. So in red or orange, we see a maple syrup that has a flavor defect. In yellow, we see the probability of having a very mild flavor defect. And in green, we have regular maple syrup. So now by adding drops of maple sap to the nanoparticles, we can predict the classification of maple syrup. And this has much more value to the producers. So what we've done is that we created a test kit that we've deployed in the field, and that is now commercialized by a local enterprise where there's gold nanoparticles in these solutions, and that we add maple sap to it, and then we can have the color chart here that correlates, in this case, a number of drops added with the sugar content of the maple sap. And thus, we can have a prediction using the color scheme of red being a high chance of having a flavor defect, to yellow that has a minor chance of flavor defect, to green that has no chance of a flavor defect. So now it gives the producers a tool to predict the quality of the maple syrup. But now where is the maple syrup flavor defect come from? So what we have done, and I will switch away from Raman spectroscopy for a minute, we have used SPME GCMS. And in this technique, what we've done is we microsample the headspace of more than 100 maple syrup to differentiate between the off-flavored one, the budding flavor with the regular flavored ones. So we analyzed the GCMS traces of these maple syrup, and we listed 42 compounds that were statistically different between maple syrup of classes regular or 0 and classes off flavor or checkmark R5. What we saw is there was a lot of pyrazine in small organic molecules, and the vast majority of those were more prevalent in off-flavored maple syrup, while only 3 were distinctive of regular flavored maple syrup. So we applied, in this case, principal component analysis to see if there is a classification between the different syrup and the compounds detected. And what we see is that there's a minor correlation between the molecular content and the maple syrup grading using principal component analysis. So this algorithm is not powerful enough to fully discriminate between the different classes of the molecules. So we've tried a different set of algorithms. And what we see here is we try to use a decision tree, support vector machine, neural networks, and partial least square discriminant analysis. And they all perform quite well and quite similarly, actually, quite honestly. What we saw is that actually the best balance between the predicted value of accuracy and for both the regular and the off-flavored was obtained with the neural network. In some cases, decision tree and support vector machine were better to detect the regular ones, but they perform worse for the off-flavored ones, while the PLS discriminant analysis did the opposite. So the neural network was the most equilibrated outcome of these algorithms. And what we saw is that we could also predict, use the molecules as predictors. And the highest predictor of off-flavored maple syrup was 2,3-dimethyl ethyl pyrazine. And this molecule actually smells and tastes like burnt popcorn and roasted cocoa. So that's actually not typical of maple syrup, and that gives us an indication that this molecule could be at the origin of the flavor defect. In the last 2 or 3 minutes that I have, I want to show how we can use Raman spectroscopy to be able to classify maple syrup in more ways. So what we can do in this case is use normal Raman spectroscopy at the laser wavelength of 785 nanometers, shine the laser light in the maple syrup, and see a Raman spectrum that has a complex convolution of different type of molecules. The goal of this is to be able to detect and quantify adulterant, so essentially molecules that could have been added illicitly to the maple syrup. We want to identify the maple syrup type, quantify the sugar content, and calculate the transmittance, which are these 3 different here are the classification of maple syrup. And we want to use machine learning, of course, to be able to predict these outputs. So we can see that there is differences in the Raman spectrum of the different categories that we have here of golden, amber, dark, and very dark. These categories are based on transmittance. And we can see that the low wave number region here has a big difference between these categories. If we just apply the Raman spectrum that is unprocessed here to try to calculate the transmittance, we see that there's only a minor correlation between the intensity and transmittance. And if we apply principal component analysis, we see that there's a good but not perfect separation between transmittance and the classification of maple syrup using Raman spectroscopy. If we apply a more complex algorithm like a neural network, it does really well for very dark and amber maple syrups, but it does poorly with golden and dark with only 60% accuracy. So this data set was done on about 100 maple syrup. So what we're doing at the moment is increasing the sample number to be able to have better predictive value and also compare different type of algorithms to improve on that. We can use the Raman spectra to quantify sugar. So in this case here, we've used a random forest regression model to be able to create a calibration curve or a training data set. And we tested that with the other part of the data set, and we see that we have about a 3% error in the sugar content of maple syrup. We do aim at 0.1, so we need to improve that, and we're working on different models to increase the accuracy to 0.1%. So overall, in conclusion, what I hope you was able to convey it was that machine learning has a great potential for sensing in predicting, classifying, and clustering molecules or group of molecules for analytical purposes. While it has great potential, the potential is not fully deployed yet. So while we've made great progress, I've shown some examples here that the performance is still not to the maximum that we expect. I've shown applications in different areas, so in neurosciences, in clinical assays, and food and beverage grading. And one of the biggest challenges I see ahead is the development of a robust algorithm or bunch of robust algorithms that can work in complex environment. So the complex environment will have circumstances where molecules will change that we did not train for. And this is where it puts a lot of burden on the machine learning algorithm. And then finally, I would like to thank a lot of the people that actually work in the group. So you can see here from the picture, we have a very diverse group of people coming from all over the world. We have people from North America, Asia, Europe, and sometimes also Northern Africa. So if people are interested in working with us, please don't hesitate to contact us. I also need to thank the funding agencies. And thank you very much for the invitation and for your attention.
Thank you, Dr. Raman. We have minutes for questions. So if anyone has a question, please write in the chat or open your microphone and comment, please. Okay, in the chat, we have a question. Let me see.
Okay, yeah, I've opened it. So
Guillermo Arnolfo, question: is there any relationship between the read number and the morphology of the nanostars in terms of fractal or multifractal dimensions of that object?
yeah, this is a great question, and this is something we have not looked at yet. But there could be relation because if you increase a Reynolds number, it will change the turbulence, and thus you could have higher fractal dimensions if it's more turbulent. Because given the quickness at which the particles are synthesized, I would suspect that there is higher fractal dimensions with higher Reynolds number. But this is not something we have investigated yet. But yes, I think we should look at that.
Okay, thank you. So I will wait till the public write, please, or comment. Dr. Guillermo says, thanks very much.
My pleasure.
I have a question, Doctor. In the Raman, the smooth noise isn't has you lose relevant information?
Yeah, so well, there can be information in the noise. So there's always a question that we ask ourselves: should we or not smooth the spectrum? And sometimes we do, and sometimes we don't. The way we assess that is that we do both with smoothing and without smoothing, and we compare the prediction value. So in the case of low noise signal, it has a big impact. And for single molecule detection regime, we oftentimes don't even smooth the spectrum because we get more accuracy without smoothing, so with more noise. Because sometimes there is some features that are hidden in the noise that can be picked up with the machine learning algorithm.
Okay, thank you. Anyone has questions? If you have comments, please allow me to share, Doctor, the certificate. So please, thank you.
Yep.
Mm, the certificate, moment please. Yeah. The certificate that will be sent to Dr. Fonsamazan later, and is written in Spanish, but I read in English.
Yep.
The Department of Chemistry and the Analytical Chemistry area of the Universidad Autónoma Metropolitana, certified at Dr. Jean-François Masson for your lecture machine learning of methods for surface enhanced Raman scattering sensors in the framework of the first international webinar of the analytical chemistry area, and held on for the 1st of December of 1994. Signed, Dr. Jorge Garza Holguín, held on the Department of Chemistry, and Dr. Guillermo Vázquez Coutinho, held in the Analytical Chemistry area. Thank you again, Doctor.
Muchas gracias por la invitación.
Gracias por aceptar. Mientras tanto, nosotros vamos a hacer una breve pausa en lo que entramos a la siguiente sala para continuar con nuestro taller de inteligencia artificial. Muchas gracias. Thank you, doctor.
Yep. Chao, hasta la próxima.
Hasta la próxima. Gracias.
De nada.